Welcome everyone to PhD Defense. We have here our PhD candidate, Josefina Lacasa. So she is today presenting her PhD dissertation, Rethinking Current Nutrition Diagnosis Models. And we usually, as a kind of a late tradition from our team, we like to start, a little bit of the history. And we did that kind of a summary because I'm getting out quickly. So it's good to have a summary recap. Josefina started here early in 2019. She came as an undergrad research and exchange with the University of Buenos Aires. And then she was working during that year, taking some classes here. And at the same time, she was working on a chapter, in fact, for her undergrad thesis that was published also. And then immediately after, we start thinking about the idea of doing a master's. And then COVID hit, and then she came after COVID, and then it was immediately fast, rapid program. And went through, not only a PhD in agronomy, moving from a master's to a PhD, but also getting a master's in statistics. She got a master in statistics, working also with Trevor Heffley and the team. So, and today she's kind of a closing in some way, this kind of a stages of getting degrees, at least from this house.
Reporting progress.
I'm not trying to close any doors in case if you want to get more degrees in the future. But I want to show one slide. And we usually do this all the time with all the students. And I usually try to do it like I try to recap a little bit because things are moving so fast and sometimes we just tend to forget. She was guessing that the first term of her name is going to be joyful, because if you can find a picture of her that she's not smiling, I'm challenging you. So in all the pictures that we found, she's smiling. So she's usually very optimistic, although she is cautious, I will put in some weight, but very optimistic, very honest, sincere, very enthusiastic. The idea of being a facilitator, I put it because in our team, she was really instrumental on facilitating and helping many research scholars that they were coming to do field experiences, and she was implementing our workshops for them, research scholars, and that is something that is, a high recognition, and then the tradition continues because, now Francisco keep moving that, and then hopefully we will be continuing that tradition. So it's something important for younger generations. Very creative, imaginative, novel, and then the last part is adaptable because she's very good in adapting to the changes or the swings that the advisor might say something, and then she's saying, do I need to do it? And I'm like, you can do it. And she finally, she delivers all the time. So, I'm never concerned. And then it has been a pleasure to have Josefina in our team. One of the best students by far. A pleasure to work with her. And then today what she's planning to do is just to show us a recap of her PhD dissertation. So I'll let Josefina to do all the talking here. Thanks.
Thank you, Ignacio.
If you try, just one. Once you do once.
I can use the mouse. Then see. Yeah. No. That's okay.
I can pass it for you.
Let me see. Here you go. Yeah. Okay. Well, thank you. Well, as Ignacio said, I'm gonna be presenting my dissertation. That is basically, it has this is an outline. It has two parts, one more like stats part and one more like the metrics we use for phenotyping the crop nutritional status. But it's all about the methods, the models we use to diagnose the crops and how they're doing in terms of nitrogen, especially nitrogen status. So the first two chapters I'm gonna be presenting are more on the stats side, and the last one is more on the crop physiology metrics we have to consider side of things. And there's one extra chapter I'm not presenting today, just for the sake of time. Now this is more about nutrition, but we're gonna be focusing mostly on nitrogen, even though our models can be applied to other nutrients like phosphorus or potassium. So nitrogen, I think we all know in this room, is very important for plant growth. It takes up most of the photosynthetic apparatus, etc. And a very important point, especially for making fertilizer recommendations, is that the requirements of nitrogen are proportional to crop growth. That's why here I'm showing this figure that is basically describing nitrogen uptake as a function of biomass. So basically, with an idea that the nitrogen uptake is driven by crop growth, right? So we usually have this mental model in agronomy where we represent the nitrogen requirements to achieve a target yield with the size of the box, and then with the figure we saw before, this box would be way bigger if the yield was way bigger too, and it would be smaller if we had low yields that we were expecting. So usually we can fill up this box partially with nitrogen coming from the soil. And the rest in modern agriculture, we do by fertilizer, right? We fill it with fertilizer. The thing is, we could be very good and match exactly how much nitrogen we need, or we could actually fertilize excess nitrogen, and the problem with that is that it can actually pollute groundwater, produce greenhouse gases, and it ends up increasing the cost of the farmer. So we really want to know what the size of the box is, so that we fertilize and we get as much yield as we can, but we don't fertilize in excess, right? So to answer this question, how big is this box? We create models that are basically simplifications of reality, right? And then here I put the definition of a model by Cambridge Dictionary. It's just a simple description, and the simpler you get, the better. But you want to use this to use in predictions of what might happen. That is, how much nitrogen I need. And then in this thesis, especially, we use a lot of stat models that are just adding extra assumptions that let us make have more possibilities for inference. So with that, the general objective of this thesis was to revise the standard methods for phenotyping crop nutritional status for production and breeding applications. And then, as I said before, this has a more stats side and a more revising the metrics that help us quantify the crop nutritional status. So that is part one of the introduction, and now comes part two of the introduction, which is talking about this model that is going to come up in all the chapters. And that's why I want you guys to understand it really well. It's the critical nitrogen dilution curve, and it's used a lot to diagnose the crop nutritional status, and basically to synchronize end supply with end demand, and that's to reduce the environmental impact. That's why this is really good for sustainability if we apply this model correctly and use it for fertilizer management. So the experiments we carry out to investigate these dilution curves are basically involving several nitrogen rates. So this is how a field might look from the sky with 5 nitrogen rates. And then we go to a field we sample biomass and nitrogen concentration. And once we have the data and we plot it in R, for example, we could see for just one observation moment, we could see this type of response. So biomass versus nitrogen. And from now on, I'm gonna be showing biomass as W because it's simpler. And we usually describe this with a linear plateau type of response. That means that biomass is responsive to nitrogen up to a certain point, that is the critical nitrogen concentration, and then it stays flat, and that is the maximum biomass. That's just for one observation moment, and that's what we normally learn in agronomy, right? Now for this model, we want to describe nitrogen, and then this is gonna look kind of odd, but it's gonna make sense in a few slides. And we're gonna flip the axis, and now we have nitrogen versus biomass, and we have the same parameters just on the other axis, right? Because remember, this is just one observation moment. If we go now to the field many times, this was one, go another time, right? We go many times, and you will see that biomass is increasing. You're moving to the right because your crop is basically growing. Nitrogen is being diluted. That's what the critical nitrogen dilution curve is describing. And we can actually, if we fit all these curves, right? And now remember that we had the critical nitrogen on the y-axis. It's being also diluted. And that's the critical nitrogen dilution curve is actually connecting all the critical nitrogens. That's why looks like that. And it's basically dividing the inefficient points that are the white points with the, in this case, luxury consumption points, right? And we describe this with a negative power law function that has, again, nitrogen here. That's why we wanted to have it in the y-axis. And it's explained as a function of biomass and two parameters, A1 and A2. A1 and A2 basically describe the shape of the curve. So they're gonna really have an impact, the estimates of these parameters gonna really have an impact on whether you that your diagnosis is that your crop is deficient or not. So with that was the introduction. Now we're gonna start with more stats chapters, comparing the statistical methods to fit these curves. So the standard framework it was introduced in 1994, and it's been used a lot since. It basically fits two models sequentially. So fits one, takes the coefficients, and fits them as data in another model. So what this might look like is you plug your data, you get your coefficients, you do it again. This for each observation moment or for each time you went to the field, and you're basically fitting a linear plateau model. And then you take those coefficients and you fit them as data in your own model. The thing here is that you're using them as data and you're basically assuming that they are correct, that your estimation was 100% accurate and right, which we know it's not always the case, and it's usually never the case. So after that, in 2020, Marcos et al. Presented a hierarchical model that is basically connecting the linear plateau model and the negative power law model in a single hierarchical model, and then you propagate uncertainty correctly compared to other model. And because basically you're connecting these two in different levels of the model, right? The critical nitrogen and the maximum biomass. So just as a summary, the highlight here is that we have two very used statistical methods. One is a sequential method that is in 2 steps, fits 2 different models, and the other one's a hierarchical method, fits just one model in a single step. One is frequentist, one is Bayesian. And what we wanted to do here is, since we have these two methods that haven't been compared yet, even though the Bayesian framework is being used a lot now, we wanted to evaluate both frameworks under varying scenarios of data quality and sample size, and then actually assess the practical consequences of choosing one over the other. So for that, we did a case study with field data and a simulation study. Today, just for the sake of time, I'm not going to be presenting the field data example, just a simulation study. And that is, I'm going to be presenting also the idea of the simulation study. We use it usually in statistics to compare different methods, where we start from a baseline, like the truth that we know. So we have a known intercept, slope, and we simulate data, but we simulate data with some noise, right? And then we fit different statistical methods and estimate the intercept and slope again. And then the closer you get to the ones that started your simulation, depending on your evaluation metrics, but the closer you get, usually the better your model your method is. So that's why we use this simulation study to compare the two frameworks with each other. So for that, now this dilution curve is a little bit more complex than an intercept and slope model, but we basically started from this reference curve with values for A1 and A2 that made sense from the data that is published in the literature. We also use slopes and maximum biomass, etc., that made sense with the literature. And with that, we basically simulated data that might look like this, for example, for one simulated experiment. And we did this actually for varying data quality. And we name here data quality as the information the data has to estimate critical nitrogen. We're gonna explain more about this, but in a way, we basically simulated 3 different cases of data quality. And the data quality had a lot to do with the distribution of the data to estimate the critical nitrogen. And then, so we had 3 different data qualities. We had 3 different observation times, as if you went 4, 8, or 16 times to the field. And 3 different nitrogen rates, as if you design an experiment with 3, 4, or 5 different treatments of nitrogen. So that gives us 27 total scenarios, and we simulated each 1,000 times. And then we fitted the models. Remember, sequential was basically just taking the coefficients for each observation moment and fitting them to the negative power law. And then the hierarchical was just fitting a hierarchical Bayesian model all at once. We use 4 metrics, so relative root mean square error, percentage bias error, coverage probability, and the difference in N uptake to reach critical nitrogen. We use these metrics to evaluate our different methods. And what we got was that the hierarchical framework was better, especially for cases with low quality or small data. Actually, for the cases where the data actually included a lot of information and was very informative, the sequential method did fine in terms of the estimates of A1 and A2. But still, we recommend using the hierarchical framework. From its properties, it has lower root mean square error, lower bias, higher coverage probability, and actually it had a very interesting environmental impact, potential impact in the in the sense that it actually estimated the sequential estimated higher nitrogen requirements with a positive bias. And it could actually estimate between 300 and 100 kilograms of nitrogen per hectare more than the theoretical. So with that, our conclusions in this chapter were that the standard sequential framework should be avoided. And that is not only for the dilution curve, but honestly, it's not a good practice to fit two models in sequence in general. This is just a demonstration of one case. And then that the environmental impact results also showed us that transitioning from this sequential to a hierarchical framework is actually a pretty cost-effective way to increase sustainability. And what is next, and that's the next chapter, is that actually with the hierarchical model, you can include further levels to a model. And it gives you more possibilities to make more custom-made models if you want, in a simple or programming accessible way. So this second chapter is kind of derived from the first one. And it's basically about rethinking some of our statistical workflow. For example, the propagation of uncertainty that we saw in the first chapter. So the problem here is basically we come from the first chapter, the kind of the paradigm has changed. We're now fitting these Bayesian hierarchical models, and this actually allows us to change a lot of things. So our objectives here were to rethink some of our model fitting techniques and actually to feature the relevance of propagating and quantifying uncertainty correctly. So one thing that I did not introduce very well in the first chapter was the fact that when we were having this sequential framework, a very common technique was to filter the data and basically leave all the data from observations out, where the estimation algorithm didn't converge. So your NLS function in R didn't converge, didn't find estimates for critical nitrogen and maximum biomass. Or basically, archaic information criteria was telling you that is AIC, was telling you that a simple intercept and slope model could explain your data just as well or better than the nonlinear curve here. And that could be this situation B, for example. This is showing two situations you might encounter, and here your model is probably gonna fit the data really well. And here, even though the underlying model is this one, it could be probably explained just as well with a simple intercept and slope model. The avoiding this data cleaning or data filtering is actually good because it increases your sample size. You don't have to filter any data anymore. I mean, you don't have to. You can discuss if there are some that you should remove or not, or if you should include them all, but it's not a requirement anymore, because now that it's a hierarchical framework and you're estimating everything at once, you basically imagine this is your data frame, and you have yield or biomass and nitrogen, and the rest are all NAs. The rest are all unknown variables that you're trying to estimate. And the thing we were doing before with the sequential model was just imputing, right, the estimates here as if they were data, as if this was what you collected in a field, which is actually not. It's like if these data were missing in a way, right? So that's a good thing. So these are all missing and they need to be estimated. And then with a hierarchical framework, you can you don't have the need to filter out data anymore. And just as a demonstration, this is not simulation study or anything. It's just one case, just to highlight this importance. So this is an example of a curve fitted with all the data and another one fitted with filtered data. And you will see that with all the data, your credible intervals are narrower, and actually it also impacts on the estimated parameters. So this is also showing the posteriors of A1 and A2. And so basically since there is no need to filter out data anymore, as long as you have good amount of data with information, it has some advantages in terms of reducing uncertainty. And then last in this chapter, we saw that we could incorporate more levels to this model. We saw that the propagation of uncertainty actually avoids bias, loss of accuracy, chapter 1, but also that you cannot yield as a level, for example. And this is, again, just an illustration, but you could actually get probabilistic inference from the probability of yield loss, for example, just adding it to the same model in JAX. So to finish up with this more stats part of the dissertation, I want to highlight some parts, and that is that we need to start rethinking our stat workflow in general, and that this change towards hierarchical models is actually pretty good because it gives us a lot of alternatives to solve problems in a pretty accessible way from a programming standpoint, and we can actually propagate uncertainty correctly. And now the last chapter I'm going to present today is more on the crop physiology side, and it's a revisionist analysis for phenotyping crop nutritional status in wheat. So wheat is, I was showing pictures of corn before, but wheat is also a very important grass, and nitrogen fertilizer in wheat is very important also. But still we are trying to reduce N inputs, right? To increase sustainability, reduce costs. And in this context, crop breeding is actually a pretty cost-effective strategy to reduce N inputs by breeding for crops that recover nitrogen better or that are more efficient in using that nitrogen to produce biomass or yields. So the thing is that breeders are slowly starting to incorporate this into their criteria. But what the metric they're using is mostly NUE, that is nitrogen use efficiency. And that is the ratio between yield or sometimes biomass and available N. It can be further dissected into nitrogen utilization efficiency and nitrogen uptake efficiency or recovery efficiency. And in this chapter, we're mostly focusing on NUTE. That is mostly because it's a more internal efficiency, and it was also the data we had. And so the thing with NUE or NUE derived quantities is that it can be misleading. I'm gonna be presenting NNI in a while now, but it can be misleading because remember that this was the line that is showing insufficiency, right? The critical nitrogen dilution curve. So for two different genotypes, for example, A and B, If you make the calculations of NUE, that is here yield divided by N uptake, you would say that NUE is more efficient for B because it produce more biomass with less proportion of nitrogen. But actually, in terms of nitrogen nutrition, they are both on the line and they are both equally nitrogen sufficient. It could be, for example, imagine that you have two genotypes that have different time to anthesis, and then one of them had more time to intercept radiation, that is energy, to produce biomass, and then had greater biomass. And greater biomass basically means N dilution, right? That is what the whole nitrogen dilution curve is about. And then this one might not be more efficient, it just produce more biomass for another reason, right? And then NUE can be kind of misleading in that sense. It could have a third example where it might look just as efficient as B, but actually the nutritional status is much lower, right? And to describe this nutritional status, we have NNI, that is the nitrogen nutrition index, and it's another application of the dilution curve. And it's basically the ratio between actual N, so the nitrogen you measure in the field, and critical N. And the way you calculate this is basically, again, going to a field, sampling nitrogen biomass, and then you get, for example, this point, but you already fitted your curve, you already know what your parameters are. And then with that, you estimate critical N, and that is basically just putting 5, that is your biomass here, and you estimate the critical nitrogen for that point of biomass. And you end up just estimating NNI as the ratio between these two. So in that way, NNI is telling you how far or not you are from the dilution curve. If you're below 1, you're deficient. If you're just 1, you're sufficient, and above 1 is basically luxury consumption. So, brief summary, the common metrics that we could use to describe the, actually to assess a breeding program for the nitrogen use could be NUE. In this case, we're using NUTE and NNI. And the most important part, what we really care about is if they consider the allometric relationship between nitrogen and biomass or not. And that's the whole point of this chapter, is comparing them because we could be missing out on some insights if we just disregarded the fact that nitrogen and biomass are actually do have an allometric relationship. So basically in this chapter, we're trying to assess this problem, that the breeders need some tools and metrics to phenotype crop nutritional status, but currently they're using NUE based metrics, but this could be misleading conclusions. So we are basically analyzing the use of NNI potentially for phenotyping the crop nutritional status. And then we're revising historical changes in NUE versus NNI. And so for the first goal, we had field experiments carried out in France with modern genotypes from a mapping population. And for the second goal, for more revisionist objective, we're using more than 200 genotypes that were released between 1969 and 2010. And here we're basically going to a field with under high N environments, low N environments, measuring everything you need to calculate NUE and NNI and yield and grain protein. And the statistical models we fit, I'm just showing the models for the expected values, but we're basically describing grain yield as a function of grain number, grain weight, and cultivar environment as random effects. And then for second objectives, we're using NUE, NNI, and NNI efficiency, kind of, that is the ratio between NNI and yield and NNI, as a function of the year of release, cultivar, and environment. So for the first one that we had, remember, we were describing yield with grain weight and grain number. This figure is showing this relationship with NNI, with yield, and a lot of things, but I'm gonna guide you through it. This is showing grain weight and grain number. And these lines here are the ISO lines of yield. So basically, each point on this line is the same yield. And for example, here you have very few grains, but very heavy grains. That's why it's yielding 4 tons per hectare. And here you have a lot of grains, but very small, and that's why it's also yielding 4 tons per hectare. And the colors are basically showing NNI that correspond to the N environments. And basically, when you increase NNI, you're increasing your yields because you're passing through these ISO yield lines. And mostly because of increasing your grain number. So that's basically, NNI was mostly associated with grain number, and grain weight a little bit, but mostly grain number. So that's an important message from this one. And for the second objective, where we had the revisionist historical analysis, we found the typical what's published already, that there was an increase in NUE, well, in this case, NUTE. Now, when we analyzed the changes in NNI, we didn't find, so basically the nutritional status, with a big assumption that the dilution curve didn't change historically. But anyways, the nutritional status remained approximately constant, or actually decreased a little bit. These are showing the 95% confidence intervals. And then when we looked at NNI efficiency, we found a slight increase, although a little bit relatively smaller than the one in NUE. So this means probably part of this is given by the N dilution, and part of this is actual gains in the metabolic efficiency of the use of nitrogen. But basically, these conclusions change depending on what metric you use. So if you use NUE, you're basically saying, okay, we did great, we increased our end use efficiency a lot. And if you use the NNI, if you include this allometric relationship, you know that you did some increases, but there might be some traits that you still can exploit some more in terms of the metabolic use of nitrogen. So with that, we say NNI is great, but also very labor intensive. We should include it in our breeding programs, but we also know that it takes a lot of time and money to go and sample to the field at flowering whatsoever. So possible solutions for this are proximal and remote sensing techniques, and depending on the target plant process and the specific portion of the canopy that we want to target, we could use, for example, drones or planes, but also going to a field if we want to phenotype the lower portion of the canopy that we actually know might be very important for yield gains. Not so much the upper part, but the lower part, and how they maintain nitrogen and how those leaves nutritional status is. And in the future, designing robots that can actually automate this process, that also takes a lot of time, but it's the only way of targeting some plant processes more specifically. So with that, in this chapter, what we learn is basically that the allometric based metrics are can give us more insights and are thus preferred for crop breeding programs. This was from a PCA analysis I was not showing, but I left it here because I think it's very important that NUE, and you have to believe in this one, but NUE is basically not related to yield or grain protein concentration, opposite to NNI, which was. And then we could actually integrate this NNI metric into breeding programs using proximal and remote sensing techniques. Just to close up, here we learned. So first, more stats, hierarchical methods, be sequential methods, and are actually a simple solution with relatively normal programming skills to propagate uncertainty and quantify uncertainty and include it into our inference. And then in the last one, basically allometric based, that means something considering this critical dilution curve. These types of metrics actually beat NUE based metrics. That is really the standard nowadays for phenotyping crops. And then future research, basically to keep elaborating these models using realistic assumptions that actually propagate and quantify uncertainty. And from the last chapter, we have to actually introduce these metrics into our phenotyping criteria, and also develop new measurement equipment that actually corresponds to a target plant trait we're targeting. For example, developing these robots that can actually save us some time going to a field and measure the lower portion of the canopy. This is kind of lame what I'm gonna show, but anyways. Yeah, this is a picture I took the first year I came, a book that Luciana gave to me, that Santiago gave to her. It's about a researcher in Argentina, and this part talks about the time he started doing science. And I feel kind of this when I'm finishing the PhD, because it's I honestly don't know how much I did scientifically, but it changed me a lot. So and that's why thank you. Thanks to my advisory committee, to Ignacio, to Trevor, to David, and Bada, because yeah, all the discussions, all the work has been great, and yeah, and Kansas State and Kansas. And in this slide, I'm not gonna talk, but thank you all, and thanks. Well, thanks to my family, to Juan, to my friends, to yeah, everyone. Done.
Okay, so thank you so much for coming. Need to make sure to take some treats because Josefina put so many treats there. There are some Argentinian sweets and probably they are getting on or out. So make sure to take something to go, and then we'll take a short break, 5 minutes probably, and then we'll be back to just to go with Josefina. Thank you for coming.